The one thing we all know about the theory of evolution is that it was proposed by Charles Darwin about 150 years ago. Well, not quite. The idea that organisms evolve was floating around for 2,000 years before Darwin and was revived a bit before his time by Jean-Baptiste Lamarck. But it didn't gain much ground because there was no obvious mechanism by which one type of animal could change into another. Lamarck suggested that maybe animals changed because they felt the need to change. It didn't sound very scientific, and with no evidence to support it, the idea didn't go very far. What Darwin did was to show a plausible mechanism by which these changes could happen. And let's not forget poor old Alfred Wallace, who came up with the same idea and published it jointly. The paper they wrote was this. Darwin had come up with what he called the principle of natural selection. These days, we tend to call this the theory of evolution as a kind of shorthand, but that's confusing, because we also use the term theory of evolution to describe the fact that organisms evolve. I want to leave the physical evidence and the proof of evolution for the next video. In this video, I just want to look at the mechanism, to see whether, sitting in our armchairs and not doing a bit of research, we can predict evolution in animals purely on the basis of what we know, that animals replicate themselves, and that the replication isn't perfect. There's always variation. Just taking these two known facts and nothing else, what do we expect might happen if we keep copying a hypothetical animal generation after generation in a changing environment? Let's say the Hypothecus lives in a tropical climate, grazing happily on grass and plants. We know from our two principles that not every Hypothecus is the same. This one has been born with a slightly longer neck. This one has slightly longer legs, the third has slightly longer claws, and the fourth has a slightly hairier body. Over time, herds of Hypothecus spread across the continent. But the climate changes and the continent dries up. Only scrubby bushes and hardy tubers can survive. The Hypothecus with the slightly longer neck can obviously get to more leaves than its neighbours. Inevitably, taller and longer-necked Hypotheca are better fed and fitter, and therefore reproduce more. A few generations later, the drought has caused overall numbers to dwindle, but there are more long-necked animals. But natural selection doesn't suddenly stop just because average neck length has increased. The longest of the long necks now has an advantage over ordinary long necks, and so the process continues. This principle is so easy to understand, you have to wonder why it's so frequently misunderstood. So let's take this one step at a time and see where the confusion lies. Surely no argument there. By which I mean children are like their parents and inherit their traits. For example, if it gets colder, animals with hairier bodies will have a slightly better chance of survival. Pretty obvious? Like genes for hairy bodies. Genes that don't confer these advantages tend not to get passed on because the animals that carry them have a lower chance of survival. So if each of these steps is blindingly obvious, then so is the conclusion. Over time, animals should change. So why don't we see it? Why does a dog always give birth to a dog, and a horse always gives birth to a horse? Well, natural selection doesn't suggest they shouldn't. What natural selection tells us is that a horse will always give birth to a horse that's very slightly different. After thousands of generations, these differences add up. If you want an example of imperceptible changes, you once looked like this. Maybe now you look something like this, but you've probably looked in a mirror every day of your life. So when did this change take place? Did you notice it? Okay, let's accept that organisms do change over time. But how do we know they change into different species, a process known as speciation? I'll leave the evidence of speciation for the next video and look at this through the example of our Hypothecus. We've seen how it can grow taller over time in order to survive a change of climate. But there may be other ways of surviving. This Hypothecus, for example, may not be able to compete well for leaves, but because of its longer claws it can dig more easily for tubers, so it would have a better chance of survival, and its genes would be passed on. The question is not whether the Hypothecus would change over time, but what could possibly stop these changes from happening. Each generational change may be tiny, but millions of years of accumulated change in a changing environment leads to two completely different animals. The question is whether their DNA would by then be so different that they could no longer breed. In the next video, we'll see if there's any physical evidence to give us the answer. Anti-evolutionists have other objections which come up time and again. Well, if you're imagining something like this, then obviously you can't. But using our theory of natural selection and breaking it down into evolutionary steps, it's easy to understand. Simple organisms would have a sensory system, like the amoeba, which can sense heat, cold, and chemicals. This could then evolve into a sensory system with a central processor, just like in insects. Individuals with better organized centralized nervous systems would be able to do more things and pass on this improved trait. The central processor would get bigger and better. Again, in stages. I won't spend time explaining the evolution of the eye here because there are a number of good videos on YouTube that do that job, including this one. No, evolution requires variation. If information is a fancy way of saying bigger ears, hairier bodies, and longer necks, then fine, we know that happens. We can see it. If information means miraculously adding completely new parts, then of course that doesn't happen, and we know why. In the next video I'll show the evidence that animals adapt existing morphology for new tasks. Trying to characterize evolution as an accident doesn't change what it is, or the evidence for it, and clearly there's nothing random about natural selection itself, because genes survive only if they're best suited to survive. Mutations are just the inevitable result of DNA that didn't make a perfect copy, and they're very common. The result is variation, not some science fiction army of mutant ninja turtles. In fact, there's new evidence that mutations don't play such an important role in natural selection, and this might be a good time to look at what we've learned since Darwin. At the time Darwin and Wallace published their paper on natural selection, Louis Pasteur was developing his pathogenic theory of medicine, the idea that germs cause disease. But it would be laughable to presume that biologists haven't learned anything new about pathogens since 1860. Of course, our knowledge has advanced. So why would our knowledge of evolution be any different? Biologists now know that mutations may not be the big engine of change. DNA can be changed by proteins which turn genes on and off, a process known as cis-regulation. Epigenetics is a huge field, but it drastically changes Darwin's premise that genes are just passively sitting there, being manipulated by environmental changes around them. Putting this very simply, biologists have discovered that DNA can exaggerate traits that are being naturally selected. Instead of being the slow and steady change that Darwin envisaged, evolution seems to happen in fits and starts. It's as if natural selection is occasionally turbocharged. Cis-regulation and epigenetics might explain why this happens. These and many other discoveries don't overturn the 19th century idea of natural selection any more than modern microbiology overturns the discoveries of Louis Pasteur, but they do show that Darwin's ideas were crude and incomplete. There's a lot more to the mechanism that drives evolution yet to be uncovered. Okay, so we've deduced from the comfort of our armchairs that evolution ought to happen. At least I hope so. Now it's time to do the research and see if these ideas are supported by physical evidence. Meet me in the next video.